The cosmos undeniably extended, empowering out and out more superior length. After this time it persisted to grow, however, at a slower rate, in the end converting into the universe we focus on as of late, that is the inflationary theory of the collectible cosmic effect, the most prominent and widely viewed hypothesis of how the cosmos began anyway. For a couple of physicists this leading theory does no longer exactly paint the evolution of our cosmos. The universe existed before that element, expanding endlessly into the past as well as into the future. Even while the cosmos is expanding nowadays, it became contracting earlier than the Big Blast. In this view, the Big Blast is not really a bang as a leap a second. Even while the contracting universe traded ways and headed out to create anew, as described through their theory, the cosmos might have to circumvent with continued improvement, discouraged by a breakdown in the far future. Then another leap. Some physicists suggested the S may be endless. This terrible situation, the usual cosmological view in which all stuff started with a huge bang. The first-class physicist Brian Cox's also challenging circumstances, the theory of how things come to evolve, that something can't emerge from nothing, adding to the stress. The James Webb Telescope has made alarming disclosures conflicting with the concept that the Big Bang could be considered the origin of the cosmos. These discoveries bring up the question, if the Big Bang wasn't the beginning of the cosmos, then what was? Should the cosmos eventually start with a detour or something most certainly unmistakable? The idea that the universe had a beginning or an evening with no yesterday as it was originally examined goes back to George Lemaitre in 1927. At the same time, it's far a less than ideal scenario to indicate that the cosmos probably had a beginning. That length of cost history has scarcely anything to do with the hot broad blast that depicted our basic cosmos. However, exceptional area matter experts, or even a minority of experts, although live with conviction that the Big Bang marks the beginning of all that stuff considered. The definition is out of the Big Blast isn't the introduction of life as we may be mindful of today. In fact, there may be a lot of proof highlighted a non-singular beginning of our cosmos. We never arrived at these conclusions based mostly on no dominant endo or over-the-top temperatures. Our cosmos is properly characterized by means of an inflationary length that occurred before the Big Blast. The Big Blast is the stop result of what took place in the direction of the culmination of progress. During improvement, the cosmos turned into most certainly void, no debris independent of no photons, just void region. Space itself became filled with a massive amount of energy at every spot. This energy changed over time, expanding in a rapid and determined pattern. As the cosmos delayed, these changes relaxed to substantial increases while new large-scale changes were made to zenith. This superposition of insecurities all through scales is a describing feature of cosmological expansion. It's for inconsistent reasons, not motive. If you lived in an expanding cosmos, you may potentially find nearby locals where an expansion reached an end or the distance between you and them delayed continuously. In short, you could attempt to obtain what happens closer to the start of a large impact before that region disappeared practically from view. It includes a little neighborhood local, in all probability no greater standard size than a human excellent hamster ball, however, likely considerably larger. The energy capability of space then at that point gets converted into matter and also radiation. This change occurs quickly, taking structure rapidly yet not instant, because the energy shut up itself turns into flume and a few photons and more. The temperature rapidly expands from just a few degrees above absolute Z to maybe around 20 Kelvin. During the identical rapid time period, due to the enormous amount of energy adjusted, all that action is near the speed of light. All particles act as radiation with enormous intensity, whether massless or massive antic. This change is called warming, marking the end of progress, and also the beginning of the period referred to as the new Big Blast. As progress continues, you'll witness a massive substitute from all previous circumstances. While the current Big Bang starts, the expanding cosmos quickly dials back after the initial image of progress in an inflationary cosmos. Location expands completely, illy with greater and expanded way regions walking away even as progress ends and the new Big Bang starts, and advanced farther areas will subside from you to an ever-growing extent. It steadily as time progresses, the portion of the cosmos in which progress ends sees the expansion rate drop, while the expanding regions surrounding it see no such drop. Under expansion, the space to any object should double after a particular length, and when that equivalent amount of time elapses, that distance doubles again endlessly once the Big Bang starts. This modification, since the expanding cosmos slows down after the initial moment of progress before the Big Blast, you may experience progress petering out with neighboring regions. Those regions where progress ends will fill with antimatter and radiation and create more slowly than the still developing locals, leaving you in the expanding neighborhood as a standard agency within spacetime. Those regions in which intensity Big Bangs uprise as far away from elite places where progress continues. Because of this, they'll swiftly subside from one another's view in the usual inflationary picture. Because of this, the progress rate changes. There may be a small chance that any universes with separate warm Big Bangs will ever interact. The area where we come to live gets rather fortunate, and progress reaches an end for us, the energy normal For space itself gets converted into an energy-dense and nearly uniform expanses of particles with the primary flaw, and also departures from consistency regarding the quantum changes that existed and were relaxed across the cosmos quicker or later of development. The high-quality energy quantum fluctuations compare initially to overdense regions, while the negative energy fluctuations get converted into primarily under regions. Those serve as the seeds of large structures. We can't see those density fluctuations currently as they were while the cosmos was primarily went by means of the extensive broad bang. There are no visible engravings we can get access from that early span after going through more connections, although we can extrapolate back to figure out the initial density fluctuations, locating something consistent with the story of cosmic improvement. The temperature fluctuations are imprinted within the cosmic microwave record CMB, offering evidence of how the Big Blast started. Yet there are different inconsistencies. Most of the CMB and our current form of cosmology were missing something, and humans can be summed up in four inconsistencies. First, on primarily large scales, the cosmos isn't always acting as expected. The light from the CMB is being lensed by means of our among us and the CMBB. That means the matter behaves like a massive lens, bending and converting the amplitude of the light in the back of it. The extent of this lensing isn't continuously consistent with our cutting-edge model, representing a superior mission for cosmology. In addition to the different sides of the equator of the CMB sky have one Mach normal temperatures, conflicting with the assumption for consistency within the cosmos's earliest degree. The possibility that the cosmos should have started dependably results in multiple inconsistencies. Third, the rate of the Hubble constant, which describes how fast the cosmos is expanding, changes depending on whether we measure it from the cosmic microwave significant past CMBB or from neighboring stars. All in all, those inconsistencies suggested we are inadequate with regards to something essential in how we select for the cosmos. One proposed solution comes from circle quantum cosmology, which derives from circle quantum gravity on the structure of life. In circle quantum cosmology, there's a smallest size of spot, the Board scale, or 1.0 x 10^35. This approach means the inner Big Bang could not exist in a cosmos described by this principle. Instead, the cosmos should never come to an infinitely small dense point near the Big Bang. In circle quantum cosmology, while the cosmos was tiny, quantum corrections and predicted a negative pressure causing a jump. On the other hand, of a peculiarity, this shows that our cosmos might have started from a first cosmos that contracted and then expanded again, similar to a phoenix rising from the cinders. While the concept of a big leap isn't totally new all the time, circle quantum cosmology provides a numerical framework to support its cyclic time. Much like the possibility of a big jump, it is also situated in H cosmology, involving in the same manner as this thought. If circle quantum cosmology is correct, the early cosmos could have had a light energy and density. This current situation should alter the CMBB, appearing as light varieties in temperature across the sky. These varieties, measured by the quality energy range, offer significant evidence of the cosmos's foundation, further supporting the chance of a jump. Normal circle quantum cosmology offers a convincing and open door to the ultramodern Big Bang version, possibly resolving a portion of the lengthy status inconsistencies in cosmology and providing insights into the origins of the cosmos. It also shows the importance of should be ready for different 5 angles and able to say something, the spirit to be fair and high counting concerning the as we delve deeper into the mysteries of the cosmos and the theories that attempt to explain its origins and evolution. We encounter a rich tapestry of ideas and discoveries that challenge our understanding of the cosmos's beginnings, from the early formulations of the Big Bang theory to contemporary advancements in cosmology and quantum physics. The quest to unravel the secrets of the cosmos has been a journey marked by profound insights and ongoing mysteries. The Big Bang theory, which emerged in the early 20th century, represents a pivotal moment in our understanding of the cosmos's origin. It posits that the cosmos began as a singular point of infinite density and temperature approximately 13.8 billion years ago. This primordial state rapidly expanded in an event known as cosmic inflation, where space itself expanded faster than the speed of light. The inflationary period lasted for an infinitesimally brief moment, but its effects set the stage for the subsequent evolution of the cosmos. During inflation, quantum fluctuations in the fabric of space-time were amplified to cosmic scales, seeding the formation of structures we observe today, such as galaxies and clusters of galaxies. These fluctuations left an imprint on the cosmic microwave background CMB radiation, which is now studied to understand the cosmos's early conditions. The discovery of the CMB in 1964 provided compelling evidence for the Big Bang theory, as it offered a snapshot of the cosmos when it was just 380,000 years old, a mere blink of an eye compared to its current age. Following the inflationary epoch, the cosmos entered a phase dominated by the interaction of elementary particles and radiation. This era, known as the Hot Big Bang, saw the cosmos cool and expand further, allowing protons and neutrons to form within the first few minutes. These nucleons eventually combined to form the first atomic nuclei in a process known as Big Bang nucleosynthesis, which laid the foundation for the cosmos's chemical composition as the cosmos continued to expand and cool. Photons decoupled from matter, creating the cosmic microwave background radiation. This faint glow permeates the cosmos and provides crucial insights into its early history. Measurements of the CMB have revealed subtle temperature fluctuations which correspond to density variations in the early cosmos. These fluctuations serve as the seeds from which galaxies and larger cosmic structures emerged through gravitational attraction over billions of years. While the Big Bang theory has provided a robust framework for understanding the cosmos's expansion and early development, it also raises profound questions about what came before and what lies beyond. The concept of cosmic inflation, for instance, suggests that our observable cosmos is just a tiny patch of a much larger cosmos, possibly one among many in a multiverse. Inflationary cosmology posits that rapid exponential expansion occurred not just once but potentially multiple times, giving rise to an ensemble of cosmoses with different physical properties. Moreover, advancements in theoretical physics such as string theory and quantum cosmology offer alternative perspectives on the cosmos's origin. String theory proposes that fundamental particles are not point-like objects but rather tiny vibrating strings of energy that exist in multiple dimensions beyond the familiar four of spacetime. This approach seeks to unify all known forces of including gravity within a single theoretical framework, although definitive experimental evidence remains elusive. Quantum cosmology, on the other hand, explores the application of quantum mechanics to the entire cosmos, including its birth and evolution. It suggests that the cosmos could have emerged from a quantum fluctuation or existed in a timeless state before experiencing a phase transition akin to a Big Bang event. These speculative ideas challenge traditional notions of causality and raise fundamental questions about the nature of existence itself. In recent decades, observational astronomy has provided unprecedented insights into the cosmos's structure and evolution. Advanced telescopes and observatories such as the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array ALMA, and the James Webb Space Telescope JWST have revolutionized our understanding of cosmic phenomena. These instruments have enabled astronomers to study galaxies, map the distribution of dark matter, and observe the afterglow of the Big Bang with unprecedented clarity. The study of dark matter and dark energy remains one of the most pressing challenges in modern cosmology. Dark matter, which constitutes about 27% of the cosmos's total energy density, is inferred from its gravitational effects on visible matter and light. It plays a crucial role in the formation and evolution of galaxies and larger cosmic structures, yet its precise nature remains elusive. Dark energy, comprising approximately 68% of the cosmos, is even more enigmatic. It is a mysterious force that permeates all of space and is responsible for the accelerated expansion of the cosmos. The discovery of dark energy in the late 1990s through observations of distant supernova revolutionized cosmology and led to the realization that the cosmos's expansion is not only continuing but accelerating over time. This finding challenged previous models of the cosmos's fate and underscored the need for new theoretical frameworks to account for its behavior on cosmic scales. One intriguing possibility is that dark energy may be related to modifications of Einstein's theory of gravity on cosmological scales, or to exotic forms of vacuum energy predicted by quantum field theory. These hypotheses represent active areas of research as scientists strive to understand the underlying physics driving the cosmos's accelerated expansion. In parallel, the study of gravitational waves has opened a new window onto the cosmos's dynamics and evolution. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects such as colliding black holes or neutron stars. The direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO marked a monumental achievement in astrophysics and confirmed a key prediction of Einstein's general theory of relativity. Gravitational wave astronomy promises to revolutionize our understanding of cosmic phenomena, offering unique insights into the mergers of black holes and neutron stars, the nature of extreme gravity, and the origins of heavy elements in the cosmos. Future observatories, such as the Laser Interferometer Space Antenna LISA, aim to detect gravitational waves from space, further expanding our observational capabilities and unlocking new discoveries.